Live in New Jersey.
Yeah.
Commute to. Yeah.
All right, so we should get started here. The panel is David Albert. This is an order of presentations, I guess, from least technical to more technical. So David Albert, Joe Silk, and I don't know whether Alan or Andre, Alan Duth, and then Andre Linde. And I think each presentation should be about 15 minutes, and that will leave us with about 40 minutes. I'm sure I'll have some questions for them, and I'm sure that you will all have some questions for them. So we'll open it up to a general discussion, and hopefully that will be fun and lively. And then I guess we have to get out of here by 9 o'clock, so let's get started.
Great. Oh, I'm sorry. Thank you so much for having me. Can people hear me? Yeah? Let me start off with a couple of disclaimers. I'm not a cosmologist, and although there are such things nowadays as philosophers of cosmology, I'm not one of those either. The reason I was invited here, insofar as I can make out, is that people think I'm a nice guy and a good sport and a more or less sensible person who happens to work in various other areas of the foundations of physics. So I'm going to take it for granted that my role here is just to display my naivete in the hope of provoking some of the people who would actually know what they're talking about to say something interesting. Good. So in that spirit, I have a couple of puzzlements, I guess, about the way that people seem to talk about probabilities in cosmology, and in cosmologies of the multiverse in particular. And I think the most useful thing to do, the only thing I can do given the short time we're all allotted here, is to present just one of those puzzlements from the beginning as clearly as I can. And maybe if people are interested, we can get into some of the other puzzlements that I have in mind in the discussion period. Good. Let me start off by talking for a minute or so about classical statistical mechanics. The fundamental postulate of statistical mechanics is often presented as something more or less like this. What you ought to suppose for the purpose of predicting a system's future behavior, if you're given only the information that the system is initially in some particular macro condition, X, is that the system is as likely to be in any one of the micro conditions compatible with that macro condition at the initial time in question, as it is to be in any other one of the micro conditions compatible with that macro condition at the initial time in question. That's more or less what the postulate amounts to, I think, in the imagination of most physicists, and that, to be sure, has a very innocent ring to it. It sounds very much, when you first hear it, as if it's instructing you to do nothing more than to attend very carefully to what you mean, to attend very carefully to what you're saying, when you say that all you know of the system in question, at the time in question, is that it's in this or that particular macro condition, X. It sounds very much as if it's doing nothing more than reminding you that what you're saying when you say something like that, when you say something like X is the case at the time in question, it's reminding you just to attend to what you're saying when you're saying something like that. And moreover, that when you're saying that, you have no reason for believing that the system is in any particular one of the micro conditions compatible with X at the time in question. Then you have for believing that it's in any particular other one. That nothing insofar as you know at the time in question favors any particular one of those micro conditions over any particular other one. That in other words, the probability of any particular one of those micro conditions obtaining at the time in question, given the information you have, is equal to the probability of any other one obtaining at the time in question. And the main thing that I guess I want to urge on you here is that it seems to me, and I think it's fair to say that it seems to most people who think about the foundations of probability as well, that this kind of reasoning is completely wrong and sort of crazy. There's a technical reason why it's wrong, and there's a more fundamental and more important, but less often discussed reason why it's wrong too. The technical reason, which probably everybody's familiar with, just has to do with the fact that microconditions of thermodynamic systems are invariably compatible with a continuous infinity of the systems. Macro conditions are compatible with the continuous infinity of the systems. Micro conditions, so the only way of assigning equal probability to all those conditions at the time in question will be by assigning each and every one of them probability 0, and that will of course tell us nothing about how to make our predictions, and so, as everybody knows, people took to doing something else, something that looked to them to be very much in the same spirit instead. They abandoned the idea of assigning probabilities to individual microconditions and took instead to stipulating that the probability assigned to any finite region of the phase space, which is entirely compatible with the macro condition in question under the epistemic circumstances I described above, ought to be proportional to the standard Lebesgue measure of the points within that region in the phase space. But, as everybody knows, I think, there's a problem with that, or there's a problem with the thought that that's innocent as well. The problem is that there's in general an infinity of different ways of putting a measure on any given uncountably infinite set of points, and there's no way of arguing that any particular one of those measures represents a truer or more natural or more compelling measure of the number or the amount or the quantity of points in any such set than any other one of those measures does. And anyway, as I mentioned above, and this is what I'd sort of like to foreground in this part of the discussion, there's a much more fundamental problem. There's something completely insane, if you think about it, about the thought that probabilities of the kind that we've been talking about here, probabilities that might somehow explain actual physical regularities out there in the world, like the laws of thermodynamics. There ought to have been a vivid sense from the word go that this was way, way too easy, that we were getting something here for absolutely nothing. We ought to have been asking ourselves from the outset how we can possibly have gone in a single magical step from I have no clue to precise numerical assignments of probabilities. Forget about all the stuff I've been talking about for the past few minutes. Suppose that there was no problem with the measures. Suppose that there was some unique and natural and well-defined way of expressing, by means of a distribution function, the fact that nothing in our epistemic situation favors any particular one of the microconditions compatible with X over any particular other one of them. So what? Can anybody seriously think that that would somehow explain the fact that the actual microscopic conditions of actual thermodynamic systems are statistically distributed in the way that they are? Can anybody seriously think that it's somehow necessary, that it's somehow a priori, that the particles that make up the material world must arrange themselves in accord with what we know, or what we happen to have looked into? Can anybody seriously think that our merely being ignorant of the exact microconditions of thermodynamic systems plays some role in bringing it about, in making it the case that, say, milk dissolves in coffee? How can that be? What can all of these guys have been up to? If probabilities have anything whatsoever to do with how things actually fall out in the world, after all, then knowing nothing whatsoever about a certain system other than its macro state, that is, other than X, can in and of itself entail nothing whatsoever about the relative probabilities of that system's being in one or another of the particular microconditions compatible with X. And if probabilities have nothing to do with how things actually fall out in the world, then they can patently play no role whatsoever in explaining the behaviors of actual physical systems. And that would seem to be all the options there are to choose from. Okay, let's see where that leaves us. There are no a priori probabilities. The very idea, when you step back and think about it, is crazy. It doesn't follow, it couldn't follow, merely from the fact that all we know of a certain system is that it's a macro condition X, that the chance of that system's being located in any particular subregion of the region of phase space that's compatible with X is proportional to the volume of that subregion. And yet, it does seem to be some sort of a fact. Or at any rate, it seems to yield correct predictions to suppose that it's some sort of a fact, that the percentage of any large collection of randomly selected X systems whose microconditions lie within any particular subregion of the X region of the phase space will be more or less proportional to the familiarly defined Lebesgue volume of that subregion. And so, the sort of fact this must be is an empirical one, a contingent one, which is just to say, a scientific one. And this, I think, is what made it possible for people, even such giants as Boltzmann, to get so confused about this. The empirically correct probability distribution in the statistical mechanical case turned out to be so simple. It turned out to be so exactly the first one that would have come out of your mouth if somebody were to have awakened you in the middle of the night and put a gun to your head and demanded that you choose a probability distribution. That the sense that it had to be that one, the sense after the fact that you knew in advance that it was that one, became overwhelming. But there is, of course, nothing about this that had to be any more than there's anything that anything that had to be the case about, say, the Schrödinger equation or the Newtonian law of gravitation or anything else. All of these are empirical facts, which we know not merely by thinking, but rather by looking at the world. Good. Let me say what I think this has to do with cosmology. Let's turn with all this in mind to, say, questions of cosmological fine-tuning. In the case of statistical mechanics, the philosophical confusion about the status of the probabilities, the confusion that is about whether those probabilities are the sorts of things that we get to know by means of empirical investigation or by means of a priori reasoning, that confusion doesn't end up causing any actual trouble in the ongoing everyday practice of science, because both the philosophically confused way of proceeding and the philosophically enlightened way of proceeding end up agreeing on what the numerical values of those probabilities are. But the consequences of these sorts of confusions for discussions of something like cosmological fine-tuning seem to me to be a good deal more serious, or at least potentially a good deal more serious. Cosmologists sometimes talk as if the fact that the universe has some of the particular features that it does amounts to some kind of a problem, even perhaps to some kind of a crisis. We observe, for example, that the universe is very nearly flat, or we observe that the temperature of the cosmic microwave background is very nearly uniform, or we observe that the entropy of the universe was once much lower than it is now. And we note as well that all the standard pre-inflationary Big Bang models of the early universe, that all those sorts of models have to say about these features is that the initial state of the universe just so happens to have had them. And this is sometimes said to amount to a problem because the probability of the initial state of the universes just happening to have features like that can readily be seen to be almost unimaginably tiny. Just think, people will tell you, of all the values that the initial curvature of the universe could have had. What are the chances that it would turn out to be so nearly zero? Just think of all the temperature distributions that the early universe could have had. What are the chances it would turn out to be so uniform? Just think of all the different micro conditions in which the universe might have come into being. What are the chances that they would turn out to be one of the very small set of low entropy ones? And inflationary theories, and theories that claim that there are a multitude of universes other than and different from the one that we see, are sometimes presented as a way of addressing or ameliorating crises like that. But this kind of talk, given the considerations that we've just been through, ought to give us pause. If somebody tells us that certain broad qualitative features of the universe are enormously unlikely, the first thing we ought to be asking is exactly where it is that this person gets his ideas about what's likely and what isn't. Apparently he doesn't get them from looking at the world, because if that were the case, by definition, the world as a whole couldn't be unlikely. So apparently this person doesn't get them from looking at the world, because it's nothing less than the world itself that he seems to be telling us is not to be expected. But where else is he supposed to look for what those probabilities are supposed to be? The chances of things, after all, are empirical matters, no less than, say, the number of birds on Earth, or the number of galaxies in the universe, or the fundamental microscopic equations of motion. Consider a proposal for a fundamental microscopic equation of motion, F equals ma, or the Schrodinger equation, or say Newtonian laws of gravitation, or the principle of least action, or whatever you might take to be a candidate for a genuinely fundamental law of nature. And imagine that insofar as we know, the law in question can satisfactorily account for all of our empirical experience. And suppose somebody now reasons as follows: what are the chances that the fundamental law of the world should simply have turned out to be, say, exactly and precisely Schrodinger's equation, as opposed to all of the uncountable infinity of other equations that it might have been? Negligible. And this amounts to a problem. This amounts, as a matter of fact, to a crisis. This exposes our present scientific conception of the world as inadequate, and the scientific project cannot be declared to be complete until we have an explanation of how so radically unlikely an equation as Schrodinger's can possibly have been put in charge of the universe. This guy is going to strike most of us, I take it, as very badly confused. We may well be inclined to say, if you can find some simpler and more fundamental and more natural looking and more compelling fundamental principle from which, say, the Schrodinger equation can be shown to follow, then by all means, more power to you. That would be nice. That would be great. I'll be interested to see what you come up with when you're done. But your motivation for thinking that there needs to be some such deeper principle are all mixed up. Because if such a principle is eventually discovered, exactly the same sort of question, the question of why this one as opposed to all the other ones that it might have been, is obviously going to arise all over again. It is in the nature of scientific explanations that all of them eventually come to an end. And the place where they come to an end is called the fundamental laws of nature. And the business of science is to discover what those laws are. And the business of arguing on purely a priori grounds that the laws must be this or that, or that the laws are exceedingly unlikely to be this or that, is going to strike most of us, I take it, as gibberish. And so the first of the puzzlements I referred to at the beginning of my remarks is just this. I don't understand what the difference is between saying on the one hand that the chances of the universe having started out, say, flat or minuscule, given all the values that the curvature might have started out with. I don't understand the difference between saying that on the one hand and saying on the other that the chances of the universe as being quantum mechanical are minuscule, given all of the uncountable infinity of different forms that its fundamental laws might imaginably have taken. Good. I hope I haven't exceeded my time. I'll start there. Like I said, there are a couple of other questions along these lines and a couple of other questions that this evolves into, but maybe this plants enough of the seed, and if we want to, we can take it up in the question period. Thanks.
So I guess, do you have slides? Or? Okay.
Too many folders. Is a landscape.
Yeah, what are the chances it's
Yeah, just click one.
Okay, right. Now to something slightly different. Okay, I think that was you just had a great introduction to one of the issues I will run into inevitably. So let me say a few words on the multiverse. So the motivation goes something like this. We know the dominant component of the universe is dark energy. We observe a certain very small number there, 10 to the minus 10 for its density. It's in a vacuum. And the community of high-energy particle physics generally expected, and some even predicted a much larger number by some 120 factors of 10. This is said to be the worst prediction in physics. Now, this has motivated the multiverse hypothesis as an explanation of dark energy, of this great problem. And to summarize one of the components, we live in one tiny pocket where the value of the cosmic constant is consistent with our kind of life. And this is the way that the multiverse community can justify the tiny value of dark energy. However, there is a counter-view, which I'll come to in a second, but there is another great argument as well for the multiverse, and that is that inflation generically results in a multiverse. So we have the anthropic statement and a very strong scientific statement. Okay, so that is the case for, and the reason that we run into problems for many people is that this is a prediction of the multiverse that's impossible to test.
You don't say so? That it is untestable?
I'm going to quote you in a second.
Oh, you
Just
said
that,
it in there.
yeah,
It's
well,
untestable and then why name?
yes, there you are. Okay, so you said it's untestable, and
I believe that it's already tested.
and that is, we'll come to that. It may be tested, but maybe not enough. Anyway, but does this mean it's not physics? That's the question. And we had a whole conference a year or two ago on what you should do with a theory when there is no very strong empirical evidence. We can still say the theory is trustable. So here's the reason why there are skeptics about the multiverse, which is that it cannot make any predictions for basically the reason that David said there is no measure basis that we understand and can define. It can explain anything. So this is the counter argument. So let me begin then by posing the question, does it even need to be testable? Maybe not. I mean, there are some people, great scientists, Max Planck, to go Max Planck, experiment is the only means of knowledge at our disposal. Everything else is poetry and imagination. So he would not have been happy with this method of testing. But of course, Planck didn't know anything about string theory or inflation. So obviously, our standards have changed since then. Okay, so inflation does predict the multiverse. The multiverse can explain anything. So I think what we should now consider is, can we test inflation? Okay, so now there are certainly tests of inflation, but one of its major predictions is a gravity wave background. And this is preoccupying much of the community now with major experiments designed to measure this. And to summarize these experiments, we're so far with the latest data at the level of measuring temperature fluctuations to micro degrees, tens of a few micro degrees Kelvin. But to get much further, we haven't found the polarization signal, the primordial beam yet. The goal is to get down to nanokelvin, roughly hundreds or even 1,000 times better than we have now, to attack the tensor to scalar ratio of 0.01. And we have many experiments doing this. The problem that we run into is that when we try to understand where these beautiful patterns, especially the primordial pattern of the beam mode underlying anything else that's on the sky, how large it might be, we measure signals from dust and lensing, of course, of both of these polarization modes, which you heard about yesterday. The prediction is anything between 0.01, we heard about 0.001, but it could be as low as numbers about 10 to the minus 36. And that depends on the reheating temperature after inflation, primarily. And so there is no guarantee of any signal that could be detected. To my knowledge, we're not designing any experiments capable of getting down to this incredibly low level, which it might have. Now, maybe these are not the simplest inflation models that could come in here, but generic inflation could well predict a very low and unmeasurably low value. Okay, so what I'd like to discuss briefly is another direction for trying to make the basis of inflation more sound. I think we do need more tests, and this is primordial non-Gaussianity, which is it's something that should be lying out there. We know that we vary everything around us. I mean, we're totally non-Gaussian, our galaxy is, everything is that we see in the sky, but this is all due to nonlinear physics, the complexity of evolution. We have to get beyond this and look for some signal on the sky coming from inflation. And there is a beautiful estimate for one of the simplest inflation models, single-field slow roll inflation by Melonsina, which predicts a bottom line for the non-Gaussian parameter, which involves the square of the geometry fluctuation, that's why it's non-Gaussian, which just depends on the scalar spectral index and gives you a number of order 0.01. Remember, the current limits from Planck are 1,000 times larger. Now, there's no guarantee that this is going to be the ultimate limit, but it's a reasonable guess, I think, to say that when we've learned how to make predictions from more generic inflation models, that there should be some bottom line for primordial non-Gaussian. It might be larger than that, but this is a reasonably inspired guess. And so I would infer from all of this that while the B mode may be detectable, may not be detectable, non-Gaussianity from the beginning is reasonably guaranteed. It would seem to be, if you're betting on this, it would be a better bet. No guarantee that it is there. Okay. So the trouble with this is that to get this improvement of a factor of 1,000 on where we are now, you need many more modes. Okay. The best we can do with C&D, just with a few million modes on the sky, pixels on the sky basically, would be to get FNL to avoid a 10. When we go to the galaxy surveys of the future, we have hundreds of times more modes, maybe 100 million if you're really optimistic, a billion. Galaxies are a diverse bunch of things. And that means you can probably reduce your limits on FNL by an order of magnitude. That's one. But that's still 100 times larger than we'd like to get to develop this ultimate test of inflation, I would hope. We could falsify inflation this way, but by not detecting some gas, presumably. Okay, so how do you get all these modes? I just want to describe what is the most exciting challenge for us, perhaps in astronomy and cosmology now. And so the CMB, as I said, it's only two-dimensional on the sky, and which also limits what one can do with it, gives you a million modes. The LSST and future experiments, 3D tomography certainly, will get us up to perhaps 100 million modes. But the future, and you can see on the, so this is the limit from the CMB, first big damping tail. Galaxies will get us further along, but by going to higher K in the dark ages, that's really our only way to boost the number of modes. So if you can do what we are planning with current generation experiments under construction here at SKA, then this will get us to part of the way there, redshift of 25. But ideally, you're messing around with a lot of things then. You want to go earlier in the universe, midst of the dark ages. And there you find that the hydrogen clouds, the building blocks of galaxies, can be seen in absorption against the microwave background. And that's when you have your best chance of unveiling up to maybe even 1 trillion modes, okay, in principle. Roughly speaking, there are 1 million building block clouds per galaxy, so you do 1 million times better than a galaxy if you're just crudely mode counting. And so there is an experiment called Codex, being proposed to go to redshift 50. Redshift 50 means working at 30 megahertz, that's 21 centimeter absorption, and that's not easy. It turns out that you can't really do this from the Earth. There's just too much ionosphere, too much terrestrial radar, man-made interference, cell phones, whatever. The best place in the entire inner solar system is the far side of the moon, where you don't have these problems. And so this is probably where you want to go to start looking then for clouds over here in absorption against the CMB. And there's a sweet spot. After rescattering, the gas and the radiation decouple somewhat thermally, kinetically, as the universe expands. And there's a sweet spot redshift 50, which is the optimal place to look for the absorption feature. Okay, so here is a sketch, a design of an array for the far side of the moon, which is shielded from the Earth, so you don't get the man-made interference, no ionosphere. And you have a lunar rover, in this schematic design, roll out dipoles imprinted on microsheets. You need a lot of them, okay? Let me just give you a feeling for what you need. You're looking at a wavelength of 10 meters to see 21 centimeters at redshift 50. You'll get to 100 times the microwave background resolution. That's great, that's how you pick up all these modes. The open array size would be a region on the far side, 300 kilometers. It could be full of lunar rocks. We're dealing with 10-meter wavelengths, so you don't care. It doesn't need to be terribly smooth. But so you'd find a place that was suitable. And roughly speaking, you'd need millions of dipoles, roughly 300 kilometers divided by the 10 meters squared. That's like other factors. So this is technology we understand. The SKA version of this on the Earth will be built with maybe of order 100,000 antennae. And so to imagine doing this on the moon in 50 years' time, perhaps, it's not a huge jump in technology. So that's where I'm going to leave that thought for the moment. it's one way to tackle this problem of what could be the ultimate test of inflation, something that we don't have the power to do with future macro-background galaxy surveys. Okay, back to the multiverse more directly. So one way is to try to address this problem of computing the odds for the multiverse. So let me just show you one string theorist version of this, Joe Polchinski. So he said that to establish a prior, I note that the multiverse is easy to make, requires quantum mechanics relativity, that's easy. I'll start with a prior of 50%. If I consider only known theories, this pushes the odds of the multiverse close to 100%. String theory most likely predicts the multiverse. He concludes, my estimate for the likelihood that the multiverse exists is 94%. Amazing. But since then, we've had an enormous discussion of the swampland, and although I wouldn't, it's far from my field of expertise, but what is terribly clear is that it reduces the odds of finding the appropriate, since the swampland predicts all string theory solutions should be anti-de Sitter, that's not good, but to get the right one, the odds must be smaller than certainly Joe estimated. Okay, so we don't know what the odds are, and as we heard earlier, maybe we shouldn't believe the characters anyway. Okay, so let me address now one particular prediction of the multiverse that I don't like very much, but I think it's good to tackle this face on. So it's due to Max Tegmark, and he said that the leading theory for what happened in the early universe suggests that space is actually infinite, containing infinitely many exact copies of you. Now, wouldn't that be a bit sad if that were the case? I would be horrified to this exact debate going on in some other solar system somewhere else, far, far away. I think this is probably nonsense, and let me try to explain why. And so I think, this is pure speculation, but let me try this out on you. So some infinities are bigger than others, so Cantor told us. For example, irrational numbers in some, between 0 and 1, are uncountably infinite. Second order infinity, if you like. Okay, so, well, think about it. Nature is probably irrational. I mean, for example, music, right? So music consists of ratios of frequencies, basically, and maybe you could argue that would be countably finite in number, but on the other hand, we all know that there are some incredibly good pianists out there, and for that person, it's clearly more than just counting, there must be some, I don't know how to express this, but I would say that is an example of an irrational process. People are irrational too. So let me, here are two examples of irrational people. So we have to face this, and this means that there are not enough planets in the universe, because they are countable, although infinitely large, to clone their identical you, which is probably a very good thing. Okay, so, right, so moving on then. What are the alternatives to the multiverse? Okay, so I'm an astrophysicist, let me try to give you the more astrophysical version of this. So the most attractive one for a while seemed to be the big hole. Okay, so we live in some gigantic void, and this of course is accelerating as it's under density, over the collapse, the void is accelerating. And this would naturally give you the acceleration. Now, unfortunately, the supernova people have measured that there is essentially no gradient in the residuals of the acceleration they measure, and other reasons too come in, and so this certainly doesn't work. But it gives you the taste that there could be astrophysical explanations for this that I don't think we fully understand or explored, it might be a little premature to put these all aside. We should be exploring these more seriously. So there's another class of explanations. We can hope for a fundamental physics theory that would come along, and let me give an example of one. So we know there's some enormous number of vacua in the landscape. The latest number I thought was far more than 10 to the 500, 10 to the 72,000 metastable vacua in F theory, string theory. And so there's been an attempt made to classify these vacua topologically. And so it turns out, and this is, I guess, all the Calabi-Yau manifolds in this case, and if you look at the bottom, you see there's just 3. And this could correspond to what you need to make the standard model of physics, maybe. And so that, so maybe you can get away from having this vast number of parts of the landscape to something very small, which would perhaps take care from fundamental physics of the multiverse theory. So another interesting development has been that Eric Verlinde in particular has been developing the concept of gravity being emergent. And this, of course, puts us right back on the starting block. The problem for just even discussing anything like the multiverse, but the problem with this seems to be that we don't really know how gravity can emerge if it's unless there's a universe there, and then so it's a question of what came first, the chicken or the egg. And so we have this very puzzled chicken over here staring at the egg in this beautiful painting by Reed, posing his uncertainty, perhaps. Anyway, okay, so the other approach to doing away with this dark energy problem, this lambda problem, has been to try to modify gravity. Now, as of a couple of years ago, in red, these were models that had ghosts and didn't work, but there was a whole bunch of models over here that looked pretty good as possible candidates. The details have not been worked out in detail for any of them. This did change a couple of years ago when the neutron star merger was measured by LIGO and simultaneously by electromagnetic signals, gamma rays, etc. Because of the very tiny delay time between electromagnetic and the gravitational signals, one was able to rule out a large number of these models. But still, as you can see, a number that are left. And so this could be, again, I think has great potential. Many of there is a large number of people working on modified gravity to try to develop this further. So this, we heard more at this meeting about dark matter and modified gravity, but I think dark energy surely is where it's been studied the most, and maybe that would bring the biggest return if ever this were to succeed. Okay, so my view is that, 10 to the minus 120 or whatever it is, it's just another constant of nature. We have several constants that we have no idea at all we don't try to, we've almost given up explaining them, most people have. So one add one more to the list, and then maybe if there has to be an explanation, someday that will come, and maybe there's no need for explanation. Okay, right, so let me come back to Planck. He said that science cannot solve the ultimate mystery of nature, and that is because in the last analysis, we ourselves are part of the mystery that we're trying to solve. Again, you heard David say this when I said earlier, we are in the universe just like this one ensemble. How on earth can we start calculating probabilities of anything? It just makes no sense. And to quote Ellis again, the very nature of the scientific enterprise is at stake in the multiverse debate. The multiverse advocates are proposing weakening the nature of scientific proof in order to claim that multiverses provide a scientific explanation. This is a dangerous tactic because multiverses can explain anything. The answer is likely to be there is none. And ultimately, I think it all boils down to this: extraordinary claims like the multiverse require extraordinary evidence, and this is something that I don't think we have had presented yet. So, thank you.
Okay. Okay, I think it's all working. Can you hear me? Okay, good. First of all, I'd like to say that this has been a great conference so far. I hope that our session doesn't blow that completely. And would like to congratulate and thank the organizers for creating such a good conference. I gather that in these panels, part of the idea was for the speakers to take strong controversial issues, strong controversial stands that we could then argue about. I think for this multiverse panel, we have an easy job with that, because it turns out that almost anything you say about the multiverse is controversial. Just no way you can avoid it. So today I'm going to be taking the controversial position that the multiverse is a plausible scientific theory and should be considered along with other scientific theories as a possible explanation of phenomena that we really see in the actual world. I'm not going to argue that we have proven that the multiverse exists. I don't think we have. But I will argue that I think it's a perfectly sensible scientific theory that belongs on the table, and I think for the most part it has been on the table at most of the conferences that I've attended. So first issue I want to discuss is actually something which came up in Joe's last remark. He said that the multiverse is an extraordinary hypothesis that therefore should require extraordinary proof. That to me is an implicit bias, and I'll try to persuade you why. There are people like Joe who feel that thinking about a multiverse is fundamentally unscientific. And I think the idea is that's a little bit too much like a bad sci-fi movie. I would like, however, to argue exactly the opposite bias. I agree these biases, by the way, don't determine anything, but they do affect the way we think. Certainly Joe's thinking was affected by the remark that he made at the end about thinking of the multiverse as an extraordinary hypothesis. So I feel that imagining a single, unique universe is more unscientific, and basically because it looks too much like the book of Genesis. If you think about science, there's nothing, I would claim, that we know of in science, I would say absolutely nothing, which we think that we can describe in scientific terms that happens only once. If the universe is to be put in that category, it's unique. And again, it's something that's much more akin to what we hear about in religion than what we've discussed in physics. So we could describe galaxy formation in scientific terms, and there are many, many, many galaxies. We could describe star formation in scientific terms, and there are many, many, many stars. And I claim that if we can succeed in describing uniform universe formation in scientific terms, which I think is ultimately the goal of theoretical cosmology, then I think it is very natural that we should expect many, many universes. The opposite would be contrary to everything that we've seen in science. Getting down to my arguments, so many of my arguments are ones which Jill already attempted to refute, so it'll be a little backwards here, but I'll try to make my arguments and maybe say a few words refuting Joe's refutation. But I'm going to argue that there are three winds that have occurred in physics in the past decades, which are pushing us towards the multiverse. I don't think that any of these are decisive. I'm not trying to claim the multiverse is proven, but I do claim that there are reasons why scientists are starting to take the multiverse seriously, and I think they're good reasons. The first of these 3 points is that almost all inflationary models allow eternal inflation. Now maybe I should take a step back. Joe was questioning inflation itself and arguing that until we find B modes, we can't believe in inflation. I have no idea why he says that. There's lots of good evidence already for inflation, of which a tiny bit is on this wonderful curve here, where if you notice all of these data points lie very precisely on the curve that goes through them, where the theoretical curve is based on inflationary models. And there are other curves about the TE correlations and the EE correlations, all of which also just fit perfectly with the predictions of inflation. Inflation also predicts the mass density of the universe. It also predicts that there are no, or at least that non-Gaussianities are incredibly small, also all verified. So there's plenty of evidence that inflation is well on the track. If inflation did not happen, it's, I think, very clear that something very much like inflation must have happened. So I take that as a starting point, really. we find B modes, of course, that's great, but to say that we shouldn't believe in inflation until we find B modes really has no basis in reality that I can tell. Why is it that almost all inflationary models lead to eternal inflation? There are basically two forms of inflationary models, one of which is shown here, hilltop kind of inflation, what was originally called inflation. And the point is that if you think about what happens if you start a field at the top of a potential energy hill like this, you might think that after some time it would just automatically roll down to the bottom. But you can solve it exactly if you imagine the hill is quadratic. And that's not what happens. Rather, what happens is the wave packet spreads. So the large part of the wave packet approaches the bottom of the hill. But there's always a residual at the top, and it falls off exponentially with time. And in any successful inflationary model, the time constant for that exponential has to be slow compared to the exponential expansion rate. So what happens is, as the inflation goes on, the volume where the scalar field is at the top of the hill increases exponentially with time, because the exponential expansion outweighs the falling off of the hill. The other important type of inflation is what's sometimes called chaotic inflation, originally invented by Andre in 1986. The point is that if you start a scalar field high on the hill, it will lead to inflation, and if you start it high enough, it will lead to eternal inflation. The quantum fluctuations of the hill will essentially sustain the volume of space at very high values of that field. In either of the two situations here, eternal inflation could be avoided if phi starts too close to the bottom of the hill. Then you could have one-shot inflation. But both of these versions allow eternal inflation, and it's my strong instinct that if eternal inflation is allowed, it seems to be the only logical option. Its duration gives it an advantage over one-shot inflation by a factor of infinity. And infinity, I remind you, is a large number. The key point really is that if eternal inflation starts just once in all of eternity, it takes over everything. And it's hard to believe it can ever be stopped from happening once in all of eternity if it's possible. And it seems that in essentially all inflationary models, it's possible. Okay, the second item on my list is what's been talked about by others, the existence of this cosmic acceleration. It was discovered in 1998 that the universe has been accelerating rather than slowing down for the past 5 or 6 or so billion years. And the simplest explanation is that the energy density of the vacuum is positive. However, if it is positive, it's much smaller than we would have thought, because the natural estimate coming from either string theory or cutting off a field theory, the natural estimate is of the order of the Planck mass to the 4th power. And the number, the number that we need here is 120 orders of magnitude smaller than that. So from my point of view, that really is an extreme case of fine-tuning. Now, David Alpert asked from the very beginning, why should we call that fine-tuning? It's just a number, we measured it, it's what it is. What I think David was leaving out was that we theoretical physicists think that we can calculate things, even things that we have not already figured out exactly how to calculate. So we think that if we fully understood string theory, it would make a definite prediction for what the vacuum energy should be, at least for any given vacuum. And we think that if quantum field theory itself were the right answer, we would somehow be able to use that and be able to understand how to regulate the infinities and get an answer. And the key point is that the basic parameter in each of these theories is the Planck scale. That would be the cutoff of the quantum field theory, or the basic scale of string theory. And it's very hard to see how a calculation is going to lead to 10 to the minus 120 times that basic scale. And I think that's the real reason why physicists worry about fine-tuning. I don't think it's based on any abstract ideas that we know about probabilities a priori. And I think it's very well founded. So, to continue, the question is why does it have this value that's so incredibly different from the fundamental scale of the theory in which we think it belongs? And one possible answer comes about from the string theory landscape. String theory plus the multiverse does offer a possible explanation for where this number of 10 to the minus 120 might come from. And the point is that if there are a huge number of vacuum-like states, and here I took sort of the minimum estimate that has appeared in the literature. Joe pointed out that much larger numbers have also appeared in the literature, but that's fine. If it's even only this large, and if the vacuum energy ranges from what we think it would range, the order of negative, the natural scale of the theory, to positive, the natural scale of the theory, where the natural scale is m Planck to the fourth power, then we have plenty of vacua which have vacuum energies in the range of what we observe. So the problem of finding those, or at least explaining why those vacua exist, just goes away. There's still the question, of course, of why should we expect to find ourselves in such an incredibly rare kind of vacuum? And the answer that's proposed to that is a selection effect. And I think to start the explanation, you could say, suppose rho vac were as big as the typical value that this theory predicts. Then the lifetime of the universe would only be about m Planck inverse, which is about 10 to the minus 43 seconds. And by lifetime, I mean if the vacuum energy were positive, the universe would just fly apart to essentially zero energy density in that length of time. And if it were negative, the universe would just implode in that length of time. So do we believe that life can form in 10 to the minus 43 seconds? I would say that you don't need to think a lot about anthropics to come to the conclusion that no, we do not expect that life can form in 10 to the minus 43 seconds. And people who have seriously tried to estimate what rho vac is possible here, for example, Steve Weinberg, came to the conclusion that the number is in the right ballpark to explain the actual value of rho vac that we see. Those types of calculations are still very controversial. Depends what you include. But certainly it is in the right ballpark to give us a possible explanation for why the vacuum energy that we see in our universe is so incredibly small. Okay, now it has been suggested, I guess not quite exactly in these words so far tonight, but it has been suggested that using selection effects like this amounts to just giving up, throwing in the towel. I claim that that's not true. I would claim that use of a selection effect like this is both logical and scientific. Notice I stopped short of using the word correct. I'm not really claiming that we know that this is true, but I am claiming that I think it's logical and purely consistent with our views of science. I think we all accept anthropic explanations for some facts, and a number of such facts have been talked about in the community. The one that I'll use here is the fact that we find ourselves living on the surface of a planet, in spite of the fact that planetary surfaces make up an unbelievably small fraction of the volume of the universe around us. I would estimate it to be about a fraction of 10 to the minus 35. You could do your own estimate, but I'm sure you'll find a number incredibly small, like the one that I found. So why do we live in such an incredibly special place? Is it explained by divine providence, perhaps? I doubt there are many scientists who would believe that, and even fewer who would try to publish it in the Physical Review. Is it just extremely good luck that we happen to live in such a wonderful place for people to live? That doesn't seem very plausible either, I don't think. I think almost all of us, if we think about it, would admit that it's a selection effect. We live on the surface of a planet because life can evolve most easily on the surfaces of planets. Life is not, we don't believe, uniformly distributed through the visible universe that we have around us. And if it's not uniformly distributed in the visible universe around us, there's no reason why we should think it should be uniformly distributed in any theory of the multiverse. So selection effects coming from the existence of life are really part of the nature of the problem. We could say that we don't understand them that well, and that's probably true, but I think we do understand them for things that are as blanket, as simple as the question of whether or not life can evolve in 10 to the minus 43 seconds. So I think it is very fair to invoke anthropic arguments here. But I would, however, argue that anthropic explanations should be thought of as an explanation of last resort. That is, the best evidence for an anthropic explanation is the absence of a better explanation, and that's more or less what the situation at present seems to be here. So I think we should always be on the lookout for other explanations, but right now I would say the best explanation we have for why our vacuum energy is so incredibly small is this selection effect explanation. So how much time do I have left?
Well, everybody's running over. But if everybody runs over, we're going to have very little time for questions.
Okay. You know how much is filmed so far? So I can say how much I'm running over.
It's almost 8:30,
Yeah.
and we have another 15-minute talk, which leaves only 15 minutes.
Okay, so I should try to finish quickly then. Okay, there was another topic I was going to talk about, but I'll leave that out. I imagine it to be optional to begin with. I just want to close with a kind of a sociological, anecdotal discussion of the acceptance of the idea of the multiverse in the physics community. And I want to begin with a statement by Sir Martin Rees. What happened was several years ago there was a conference on the multiverse, and a reporter went around and asked several people what they thought of the actual probability of a multiverse existing. And one of the people asked was Martin Rees. He's known to many of us. His friends call him the Right Honorable Lord Rees of Ludlow. Some call him Martin. He's won a few honors. He is and still is the Astronomer Royal of Great Britain. He's the former president of the Royal Society, a former master of Trinity College, a winner of the Gruber Prize in Cosmology, the Crawford Prize, the Templeton Prize, the Isaac Newton Medal. About as many honors as you can imagine. This is only really a subset. He said that he's sufficiently confident about the multiverse to bet his dog's life on it. Now, I have to admit I've never met Martin Rees' dog.
How old is his dog?
Yeah, I don't know. How cute he is, I think, is relevant. And I don't really know. But nonetheless, I think no matter what answers we propose to those questions, it's a pretty significant bet to bet. People usually do tend to become attached to their pets. As far as I know, Martin is as warm a person as anybody else. He was probably quite attached to his pet. The second person to be interviewed is a member of our current panel, Andre Linde, who also has a nice list of awards: the Harvey Prize in Astrophysics, the Breakthrough Prize in Fundamental Physics, the Gruber Prize in Cosmology, the Dirac Medal. Andre, as I'm sure we're about to hear, is very enthusiastic about the multiverse, and he said he's so confident that he would bet his own life on the existence of the multiverse. Wasn't quite clear how the bet would be decided, but he was willing to bet that. I'd like to close with Steve Weinberg. Steve Weinberg was not actually at this meeting, but he read about it and commented about the issue later. He also has won a few prizes here and there, going up to the Nobel Prize in Physics. And he said that I have just enough confidence about the multiverse to bet. Very clever here. I really love this. He said he has just enough confidence to bet the lives of both Andre Linde and Martin Rees. I'll stop.
Yes. So I will start far. Well, first of all, I say, I completely agree with everything Alan just said. And I mean, yes, okay, because there could be some things. I do not agree with only one statement, that the volume of the universe is 10 to the 35 times greater than the surface of the planet, because surface cannot be compared with volume. Okay, all right. Now let's see. Before coming here, as usually, I checked Google, because when people talk about the multiverse, and this panel is also demonstrated, everyone has its own idea. And I decided to check Google Trends, how many people were looking for the concept of the multiverse, just checking whether it's still popular or not anymore. So what I found that interest over time continue growing. It was positive thing, so more people are interested. Then I looked more carefully and I found that most of the requests coming from Peru and from France and Chile and Argentina and Spain. Oh my God, but there is no US. I thought something is wrong. And then I checked what are the questions. Mostly it is Dragon Multiverse. Okay. So on this note, I should say that before we say, I hate multiverse, or I love multiverse. Are you talking about Dragon Multiverse? Okay. So therefore, coming to a real subject, first of all, why we're talking about multiverse? Because all the time when Alan and I and other people start thinking about inflation, our idea was to explain why it is a universe, why it is everywhere the same. You start with anything. You can start with like balloon, or you can start with a cucumber, and then it grows up, well, exponentially, and the surface becomes absolutely flat, and everything is homogeneous, and everything is produced only from quantum fluctuations. If not for quantum fluctuations, it would be absolutely smooth. So it's very, very generic, and it's unique. And it's dark. Okay, and it's again dark for me. Yes. Well, no. Okay, no. So this was normal. This was a universe, and at that time everything was cool. But then I remembered what Harry Ford said. Okay, he said that any customer can have a car painted any color that he wants, so long as it is black. Okay, so if you have a universe, it must be one universe. And why one universe? Well, because we paint it so. But if you start with a tiny ball, and which is painted like a football, and you make it inflate, then it looks like that, after that. And this part is very, very huge. And any observer looking inside will see around only white universe, and he will have a theory, trying to prove a theory that the universe must be white, and the guy living here will try to prove a theory that it must be blue, and none of them will be right. So we do not have any evidence whatsoever, it's zero, that it is painted by one color everywhere. So there is no experimental evidence, and again, that's what Alan said, zero experimental evidence in favor of a universe. If you have a generic cosmological solution, if you have a generic theory, and you want to prove that it must have been of the same color everywhere, you must prove it. Otherwise, what you're saying is a hypothesis. Now, so uniformity of the universe is explained by inflation. Exponential stretching makes it uniform. But classical stretching, as I just demonstrated, doesn't imply global uniformity. And at quantum level, usually the evidence favors something else. Inflationary universe may become, may not, depending. And so now we are going to details. So first of all, general attitude, outcome kind of. Pessimist, he will say, if each part of the multiverse is huge, we will never see other parts, so it's impossible to prove that we live in the multiverse, which is right. Okay? Optimist will say, if each part of the multiverse is huge, we will never see other parts, so it's impossible to disprove that we live in the multiverse. Same statement, two completely different conclusions. Einstein said, I would rather be an optimist and a fool than a pessimist and right. Okay, and then the scenario which say that it is a multiverse is just more general. So once again, the same argument. If you're making a statement that is anti-scientific, etc., it is an anti-scientific statement, making a statement which cannot be proven, and you cannot prove that we live in the universe. Moreover, even if one believes in a single-colored universe, quantum mechanics makes it more different. And we know already very strong evidence in favor of it, its origin of galaxies. Galaxies are created by quantum fluctuations. And this thought is so dear, even though everyone right now looking at Planck hear the data. And nevertheless, Roger Penrose tells me, nothing classical can be created from quantum. I say, what? And that's the opinion of the people who were the kings of cosmology several years ago. Actually, he left cosmology just at the time when inflation entered. So what we see that when people did not suffer through it, do not know it, They say it's just impossible. So inflation made something impossible. Let's take it seriously because we have evidence which is checked by Planck satellite, by WMAP satellite, that many different experiments were continue hearing how many people are learning about it. So the first thing is that limits of classical cosmology. It seemed to me, at least, it was like a shocking thought. The shocking thought that if you play the movie back, which is what usually people mentally quite often do, they assume that they just press it back, and it goes back to the singularity, etc. But you will never press the galaxies back into vacuum. They have been produced from vacuum. There was not a single particle, there was not a single galaxy. They do not appear from galaxies or from something else. They appeared from expanding universe with certain properties. So the movie can be played back. And the analogy here is this. You know this is famous story about Schrödinger cat. People are debating Schrödinger cat for 100 years. So whether it is really it's died at this moment or at the moment when you open the cage, etc. And people hate each other guts by saying different things about interpretation of quantum mechanics. It's still unsolved problem. Did we stop using quantum mechanics because of that? Well, thanks God, no. There was a symposium planned in Soviet Union. I know it because I was born a year later. Okay. So symposium was planned a year earlier to forbid all physics because it's completely idealistic science. And Stalin stopped it from happening 3 days before the symposium. They already killed genetics. They killed cybernetics. They did not care. They wanted to have atomic bomb. So they stopped it because they wanted a nuclear weapon, okay? So quantum mechanics, you may hate it, you may not understand, still, it's almost idealistic nature. But nevertheless, you must use it one way or another. So let's take it seriously. So let's play this movie for the cat, for the galaxies. So interesting thing, that when you play the movie back, you will see that there's no cat. Because all galaxies have been born from vacuum. So as compared to the problem, which is still not quite unsolved, quite solved philosophically, but people simply stop caring in some sense. Some still do, and me still do, about the interpretation of quantum mechanics. What we have here is quantum field theory. And quantum field theory tells you that you may not have a particle, or you may have a particle, or it may be a different particle. But we never thought that instead of particles, we may speak about galaxies. And once you start saying that particles, which you describe by everything, are quantum mechanical objects, then you need really to take seriously quantum cosmology. And in quantum cosmology, it's quite possible, every possible classical solution, or not necessarily classical solution, has its part in a wave function of the multiverse, of the universe, which tells you all possible outcomes, however strange and improbable they could be. So you cannot just avoid it. Galaxies, this is not a joking thing. And then we just start talking simple stuff. And let's take SU5, it was supersymmetric SU5. This problem is very, very old. Weinberg have found, actually there are other people have found, that there is a dozen different minima if you take into account both reactions in the Higgs field, one and another. But I'm showing you only three. This is only three of them. This is SU5. This is SU4 cross U1. This is our state. Okay. And then what people found that at high temperature only this one existed. And then when temperature drops down, these two appeared, but the tunneling, as Weinberg have shown, tunneling is impossible. So if you have such theory, how can you come to our minimum? And then I say, okay, well, that's not a problem. Because if you have high energy inflation, then quantum fluctuations bring you everywhere in all of this minimum. And then inflation stops, and some part of the universe becomes green part, some blue and some red. And what we did, in fact, we did the computer simulations. And computer simulations show you, start with the red universe, which is where you're from. And then you make these quantum fluctuations, and the quantum fluctuations overlap. Each new slide is exponentially larger than the previous one. And then the colors correspond to different minimum. Colors start forming domains which have definite color when you're already sitting at the minimum and inflation is already stopping, and then you're frozen there. And they call the Kandinsky universe because they remind me this person. And so what? Here is the red minimum, here is a green minimum, here is a blue minimum. And then at some moment it all freezes. But then what you see right now is how the universe, starting in one minimum, becomes, well, separated into pieces with different colors, which completely different physics. It is the same theory. It is not different theory. It is not, it's the same theory. But you cannot live in SU, I know about myself, I cannot live in SU5 medium, because there are no leptons, no difference between quarks and leptons in some sense. But we need to have SU3%. So you live where you can live, nothing terrible about it. Then what happened is string theory came. Okay, when string theory came, something happened which you may trust or may not trust, but I have witnessed how it all was. And the story was like that. 98. And people have found this acceleration of the universe. And string theorists say, yeah, but we don't know how to do it. Okay. And maybe it will all go away. What do you think? They ask all of these people who studied memory. Maybe you are wrong. No, but still okay. Then there are other evidence from different data, all cosmological constants is here, okay? And string theory, Ed Witten gave a talk saying that, well, unfortunately, I have no idea how we can detect this space in string theory. And when Ed Witten said so, people start getting nervous. So for the first time, string theory has any experimental prediction, and it is made by Ed Witten that we cannot explain experimental data. So this means that the first experimental prediction of string theory is wrong. Okay? Well, then people start thinking about it more. And people found suggestions, not yet a theory, not yet a construction about which you can give the life of your dog for, but it is still something which you can, maybe for cat, I'm not sure, but we think that what we have right now is a reasonably good construction which survived from 2003 to the present, which is 16 years, not being disproved, not being completely proved, but not being disproved. And several papers which were claiming that it is wrong, which were one of the bases for the swampland conjecture. I checked some of them, and all of the papers which I've checked, not all of them, but all of them, they contain silly mistakes. And I mean, I'm not a string theorist, but I can see where there's a silly mistake, which are just people lie, okay? So it's, now, I am not saying that it is proven, I'm just saying what happened is that in this class of theories, you have many different states, and many different states does not mean that they are guaranteed to exist. But there are lots of moduli, and they either form stable state, or they do not form stable state. And if they form stable state, then there are many different combinations how you can do it. And combinatorically large, this is property not necessarily of string theory. If just you have multidimensional space, there are many ways to do it if you can find it stable. So in this case, the statement is that it may be stable. And that is why people were so happy that there is this part, galaxies is destroyed, each of this minimum corresponds to one of these vacua. In this part, the universe rapidly collapsed. We cannot reliably calculate energy density in each of these vacuum. But if you have 10 to the 500 different vacuum, and you make your recalculation using your corrections, each of them shift in their positions, maybe very strongly, but if there are many of them, there is a chance that some of them will find themselves in this region. It is still not a theorem, it is still a suggestion. This suggestion, however, have not found any, well, rigorous statement saying that it is wrong. Now, what happened later, this swampland conjecture. And a possible suggestion is that instead of this vacuum, you may have, for example, quintessence potential and the simple quintessence potential, which were advocated in the first series of papers on swampland, were of this type. We checked all of the models suggested in this first series of papers. And we found that, in fact, half of them or more have been studied, explored already almost 20 years ago in our own papers. I and Renata Kalsberg studied many of them before, and we just concluded that that did not work. Now we re-studied them again, and they are ruled out at level more than 3 sigma. So it is not a theorem that it is impossible to make this swampland quintessence. It may be possible, but it is required to be proven and to get one completely constructed in string theory example of quintessence. And there is something else about it. There is a conjecture that these kind of potentials, they are valid only at a distance about Planck scale. Now, if you must have it extremely flat, then the validity is like you can move it only at the Planckian distance. And at the Planckian distance, if your final value is 10 to the minus 20, then Planckian distance from it will be still 10 to the minus 20, maybe multiplied by 2. So each of the small pieces of the potential is valid only at this 10 to the minus 20 interval. So which means that it is just like in the landscape, you have patchy picture. And that is what I think. It is not a proven statement. It's just what I expect. I'm not suggesting to you that this is something more than my conjecture. Okay? So conjecture is that you have many different pieces. Some of them may or may not survive minima. Some of them may or may not survive this kind of curves. But each of them may have different physics associated with them, because each of them is formed because of different types of compactification. So one way or another, you have a landscape. Maybe right now enhanced landscape, if we consider these additional things, maybe somewhat reduced landscape because some of the previously existing may not exist. I'm just saying that this is a picture which is a part of the game and which helps to explain the present value of the cosmological constant. And here I will say just something seemingly not relevant. I was in the Leiden, the university, for quite a while. At each floor, there is a photograph of all of these people looking at you, which were working there at different times. And Ehrenfest, the house of Ehrenfest, everybody showed you the house of Ehrenfest and explain you how his life was dark and how he committed suicide, first killing his own son. It's terrible things. There is lots of strange stories. They know everything about Ehrenfest. They did not know that in 1917, which was simultaneously the year of discovery of de Sitter solution and Great October Revolution in Russia, in this 17, he found a way to explain, or he had made a suggestion about which nobody cared. He told us that we know why our universe is, well, 4-dimensional if you measure time like extra dimension, like a part of this 4. Because in three space dimensions you have planetary systems. In 5, all of them are unstable. In 6, they are unstable. The same is for atomic systems. They are all unstable in higher dimensions. Now, if you consider smaller than 3 dimensions, 2 dimensions, 1 dimension, gravity, normal Einstein gravity, does not show any attraction between planets. So planetary systems are possible only in the universe with the dimensionality of our time. And this did not make any sense for anybody who cares, because we live in this state. Why do we need to explain? But in string theory, it is possible to have spaces of different dimensionality. And different string theorists are trying to prove a theorem or try to see whether there are some reasons why all spaces, except for this compactification, are maybe unstable, etc. Maybe there's no need to prove that they are impossible. To prove that everything else is impossible, sometimes it's more difficult than to explain why this particular part works. So this is just another thing of kind of anthropic reasoning. You may or may not take it seriously. I'm just saying that there are many other examples. And when you start thinking about the multiverse, it suggests you an option, a possibility, sometimes to use what it gives you like a free gift. You may take it, you may not take it, you may find physical, good solutions, and it will be much more preferable. But just discarding multiverse because you do not want the name, it is not something which I would consider scientific approach. Thank you.
All right, so I'd like to ask the organizers, we have a short amount of time left. Do you prefer that the panelists interact amongst themselves, or that I ask questions from the audience?
All right, so a couple of things. I'm happily surprised that remarks that I thought were going to be irrelevant to what everybody else said turned out to be less so than I had thought. The downside of that is I got both congratulated and berated for things that I didn't think that I said. Let me clear that up a little bit. The thing, when I was talking about fine-tuning issues, I mentioned flatness, I mentioned the low entropy of the universe initially, and I mentioned the uniformity of the temperature. The one thing that I didn't mention, and it wasn't an accident, was the lowness of the vacuum energy. That's because I don't think that's a case of what I was talking about. And it seems to me that you're exactly, what you said about that is exactly right. This is not a case of an a priori calculation. This is a case of a calculation from, say, quantum field theory, which we have separate empirical reason for believing, and which leads exactly as you said to a very high number. And in a case like that, we really do have a problem. And it seems to me that it's not the only imaginable one. Maybe something else is wrong. We do have a problem there, and certainly one possible solution to a problem like that is a multiverse theory together with a selection effect. So there's no disagreement there. Something that I was, and maybe things have evolved since I last heard about this, among the things that nobody mentioned, but once upon a time they used to mention as motivations, were other kinds of fine-tuning situations, flatness, low initial entropy, uniformity of the temperature, so on and so forth.
Because I do regard those as fine-tunings too. So. Good,
but you mean you regard them as in this sense similar to the vacuum energy situation? You think we have ways? You think we have empirical ways of calculating those?
Well,
say something about that.
Well, happens maybe too strong a word, but I think we do imagine that sometime in the not so distant future we will have a theory of universe creation. We in fact have such theories now. But
right.
Very crude.
And those will, and those will have the following two features. They'll be good explanations of empirical phenomena that we see, and they will entail what? They will entail less flat universes than we see, so we'll need a multiverse plus a selection effect.
Well, no, I mean, the flatness and uniformity problems are solved by inflation by itself without a multiverse.
No, but the question is, what are those problems in the first place? Unlike in the case of the vacuum energy, we have good empirical reason for believing the vacuum energy is high. What's our good empirical reason for believing that the flatness shouldn't be so low?
Well, what I'm saying is that if we imagine a theory which describes universe creation, and as an example, we might take these nothing theories that we actually have, although we don't believe them that strongly, they do not naturally produce a flat universe unless we couple them with inflation.
I see. And there are other good empirical reasons for believing in those.
Well, that's probably too strong a statement.
I see. Okay.
But what I'm saying is that no matter what theory we imagine for universe creation, it's a little hard to believe that it will just naturally, automatically lead to a universe that's flat at the level.
But this is worth pursuing. If you say it's just a little hard to believe, that could be for two different kinds of reasons. Okay. One of the reasons could be an a priori suspicion that the chances of this are just low, okay? And that's what I was claiming I don't understand, okay? The other could be something more like the vacuum energy case. We have definite empirical reasons for expecting the vacuum energy to be much, much higher than what we observe it to be, okay? Those are two very different kinds of reasoning. And when you say it just seems natural to expect that the curvature should be higher, I don't know which of those kinds of reasoning that statement is a result of.
Probably neither. I would say it's a result of experience with theories. Theories generally have some number of input parameters, and then calculations that express final answers in terms of input parameters. The flatness is, I think, the natural dimensionless expression of the flatness is the number of particles in the curvature volume, which is 10 to the 90, curvature mass 10 to the minus 90. Numbers like 10 to the minus 90 just don't come up very easily. You're manipulating factors of 2 and pi and 7 in the calculation. That's what it's based on, I would say. Other people might give you different.
Okay, this would be worth knowing. This would be worth knowing more about, and I'd be very interested to talk about it. But anyway, yeah, the reasons you said are exactly the reasons why I didn't mention vacuum energy among the fine-tuning. So insofar as I understand that, I agree with you about it completely. The other thing, and maybe I'm taking up too much time here, if I am, just tell. I mean, it was one thing about what Professor Silk said. I didn't see myself as thinking that. I mean, it seems to me a very elementary kind of philosophy of science point. If you have good empirical scientific reasons for believing A, and if A entails B, then you have good empirical scientific reasons for believing B. And to the extent that we have good empirical scientific reasons from the famous graph that you put up for believing in inflation, and to the extent that we have good empirical scientific reasons from inflation combined with quantum mechanics for believing that inflation implies eternal inflation, we have good empirical reasons for believing in a multiverse. I think that's pretty straightforward.
As a string theorist on the panel, maybe I can just say one thing, because in order to use the multiverse to explain or to make us feel not so bad about this very peculiar small value of the cosmological constant, we really need two things. One is eternal inflation, and the second is a theory like string theory that can have many different solutions, with each of those solutions having a different value of the cosmological constant that populates a large number of possible values. And in string theory, I think most people would agree that there is a huge number of solutions with unbroken supersymmetry, with either anti-de Sitter or Minkowski space as the cosmological solution. But when it comes to de Sitter space, there's quite a controversy, and there are definitely people that feel, like Andre, that there are, say, 10 to the 500, and that's more than enough to populate the space of possible cosmological constants. But there's also a substantial fraction of the community that thinks the number of de Sitter solutions in string theory, where you can really make a controllable approximation and understand what you're doing, could be 0. And I just feel compelled as the string theorist on the panel to make that point, that I don't think we really know that one of the ingredients needed for this explanation is true yet.
Yeah.
And then just to add to that, the first point, inflation does make the prediction, as you pointed out, but the trouble is inflation, I think, we're not very happy with understanding how it began. Generic initial conditions, it seems, do not lead to inflation. For that reason, I think we still need more tests, and I was proposing one. So I would be, even though it's a great phenomenological theory, we've had these in the past. The history of science tells us that, and then they get replaced by a better theory. So I think it's healthy to look for further tests.
I think that there are some scientific issues which we can discuss, communicate with each other, because none of us agree at absolutely everything. There are some regions of disagreement. There is also, of course, we do not know exactly what happens in string theory. In fact, we do not know whether string theory will be still with us like 30 years later. So we are looking for some conceptual possibilities. And what we have found in the concept of string theory landscape, one of the conceptual possibilities which was not fully explored, but which was suggested to me, for example, this idea was suggested by Sakharov in '84, before any string theory based on completely different reasoning. And he wanted to use it for cosmological constant problem. Okay, so what we need to do is to see whether there are some new possibilities in theoretical physics which can be explored without violating something which our community, after lots and lots of debating and thinking, will consider to be a reasonable scientific approach. So whatever is a reasonable scientific approach seems to us, it maybe not seemed to people like 50 years ago. And yesterday at the dinner, there was a suggestion how to overcome this difficulty. The answer was, there is always this funeral solution. Yeah. So some of us are going to be gone, and others will not care. So we'll see what happens with all these ideas.
So I would just add to that that we should be looking for theoretical solutions, but also for experimental solutions. And given that there is no possible experimental solution for the multiverse, then it's inflation that we have to thoroughly be convinced is, going in the right direction. I think we have work to do this.
And I would say there is also one other criterion which is absolutely necessary in this field, because we are all such deep thinkers, etc. But without sense of humor, we are all.
Thank you very much.